Welcome back to another HVAC-Engineering-Techie training video. Remember, these training videos are technical in nature, intended to help you with your career. So today's lesson is HVAC technical commissioning functional testing. So this is really an important video. It's the one that actually shows you how to write scripts, how to do them, how to do the functional tests, and how the functional tests actually prove performance. So you really need to understand this particular video. Remember, this is the channel that talks all things HVAC, from engineering design, construction, equipment, systems, test and balance, controls, energy, and efficiency. All right, so before we get started, I'd like to ask you a big favor. If you wouldn't mind becoming a subscribing member, if you haven't already. Now, to become it, you just hit that subscribe button down below. Give me a thumbs up if you like the videos. These are free, cost you nothing. They're painless to you. But they really help me because Google uses that data to evaluate the videos, which keeps me on the air. So I'd appreciate it. All right, let's get started on functional testing. Thanks. So technical versus process commissioning. What's the difference for functional performance testing? FPT. What's the difference? All right, so process commissioners provide functional testing by observing the control system being tested by the control contractor. It's not a problem. But it's normally just walking around watching them fail things or turn things on and off, and just making sure that things run in the right direction. You know, okay, so this heating valve opens, so it's going into heating. This cooling valve opens, so it's going into cooling. And there's nothing wrong with that. It's just that it only touches the surface. So technical commissioning creates functional test scripts and supervises the control contractor in performing these test scripts. Now, that's really important. Process CX utilizes observation as proof of performance with no backup actually showing performance of the control sequence. It's actually take my word. And that's okay, I guess, but it can end up not actually observing the true performance. Technical commissioning utilizes control data trends or system response to prove functionality of control loops. Functionality is proven by trend or point data. So we actually have a data trend that says, look, I tested it. This proves it actually works. It's not just take my word for it. I've got a document that proves it. Functional tests are the final system tests that prove the systems are complete and functional and ready for automatic operation. FPT tests the control system and the connected HVAC system operation at the same time. So we use the control system to manipulate the system and to record what happens, but it actually is testing everything. It actually tests the design, the installation, the startup, all the systems in that whole thing. It tests the whole HVAC system together. The FPT tests display all aspects of the system are correct. The system design, system construction, equipment of the system, control systems, test and balance. But FPT tests do not test system capacity. The reason that it doesn't test capacity is because capacity is so difficult to test because you can't control the environment. You know, if you could tell when a design day is going to happen, you know, it's the same temperature and humidity as the designer used, then you could actually test the capacity, but it's not there. So FPT tests the control system programming for control schedules are correct. Control set points are correct. Control resets are working correctly. Control system response and polarity are correct. Control loops are properly tuned, indicating limited hysteresis. Small settling time to set point and a fine small offset, and we'll go over all this later. FPT testing is required to verify that hidden programming within a controller provides the design intent. Programmers do not always program the exact sequence as described in their own submittal. The way this is supposed to work is the designer puts the sequence on the drawings or in the specs that he wants to happen. And then the control contractor is supposed to take that sequence and modify it to what his system requires to make that happen. So not all systems have to program exactly alike. So he should add to that sequence anything that he has to do, like exit parameters. What is the parameter for them to exit the system? Which is never in the engineer's sequence. And then that's what they put on their submittal. However, in reality, what they do, the control contractor just simply photocopy the sequences the engineer wrote and just pasted in their submittal. And the reason is they don't want to get disapproved. And then they'll just write the real sequence, whatever it takes, they'll put that in later. And that's what we're trying to discover, because we need to see that. So the tests are trying to discover the following. The required sequence response is programmed into the controller. All specified sequences are programmed and functional. All sequences of the system and their components are functional. This is why we do functional testing. FPT testing actually tests not only the control system and its sequence of controls, but also tests the system they control. So for an HVAC system, FPT tests the end result of the system operation and controllability. This is why FPT tests are the most important test of a system. It finds if funds are not available to do point-to-point and FPT testing, FPT will also indicate failed points. This just slows down the functional process and shows more test failures, but it will test everything connected. So we always do a point-to-point first to try to not have failed functional tests. So, but if you want to do a point-to-point, then you want to do real functional tests, then you're going to have a lot of failures. But that's up to whoever's signing the checks. FPT tests do not test system capacity. System capacity tests are destined to fail due to the inability to test the design conditions. Normally, FPT test. Who does the FPT test? Normally, FPT testing takes a team approach because you need the control contractor to operate the system for the test, and the commissioners needs to supervise them to verify the test results. Other possible participants in the functional testings are any commissioning team member, control contractor, owner operators, and the owner operators are a really good one to have there. If you can actually get them broken loose from their job for a while to help you do functional testing, not only does it help you, but they now learn a whole bunch about their system, and it's really good training for them. Mechanical contractor, equipment vendors. Equipment vendor may be there if it's got an exotic machine involved. Providing FPT test scripts to the control contractor to perform without the commissioning supervising the process normally does not work. Most control contractors cannot properly evaluate if an FPT test fails or passes, which is crazy. But I've had jobs when I first started this, I just give them my scripts and said, you go perform this, give me back the trends. And 30-40% show the trend showed failure, showed that your control system is not working. But the control guy just didn't know. He can't read the trend. He doesn't know what it means. So it's best for you to be there to watch them as they do them and say, well, okay, that one worked. Or, no, boy, that one didn't work. Something's really wrong. It's just much more progressive to be able to be there to supervise. Now, there are some instances where you can, like long-term trends, you're not going to supervise those, but you're going to get them back to no results. One thing about supervising a control contractor is you're training him what a good trend is or what a bad trend is, and then eventually he'll be able to figure it out for himself. When are the HVAC functional tests performed? When are they actually done? Functional tests are performed after all construction is complete. All system startup tests are complete, and the system tab has been completed. So basically, it's about right near when it's going to be occupied is when you need to test, which is a problem. Functional testing is performed after the building is on normal utility for power, water, and sewer. So the building's complete. Functional testing must be complete prior to occupancy of the building, since the test will disrupt occupant activity and may affect the test outcomes. So here's what normally happens, and we've mentioned this in the previous video, but the general contractor has missed schedule days or things that didn't get done on time, and so it begins to get longer and longer, but the actual start date, turnover date, doesn't change. So he's actually compacting the end of the schedule, which is your testing time. Now, that's why I keep telling you that functional testing is a critical path. You cannot allow a functional test to be truncated. It cannot be shortened. If you try to test, a lot of them say, well, let's just do it while it's occupied. Well, you can't do that unless the occupants don't mind the building getting run to 80, 84 degrees, down to 70, 65 degrees, pressurization changing, all these things changing. As long as they don't mind the building being totally out of control, it'd be okay. Because people don't bother our test unless we're doing an envelope pressure test. But if we're doing general tests for temperature and humidity, the people don't affect it, unless they leave doors and windows open. That can't be. But other than that, there's not a problem. Functional testing is always a critical path, and you have to pound that into the general contractor so he's fully aware that this is a critical path. Some functional tests are restricted to being performed during the appropriate season, so they may be a deferred test. So let's say you're right in the middle of summer, and you're testing all this, and you need to test economizers. Well, you really can't test an economizer in the middle of summer. Much better to do it in winter when the right season, when they can actually be used. So we normally do that as a deferred test. And so what happens, they finish and occupy the building, and then we come back in an appropriate month and run that cold test when we got cold temperature outside and prove the economizers actually work. And there's other tests also that might be deferred because something else prohibited this test from happening. Remember, site safety in performing functional test safety. It's really important to watch safety on inspections, and it's really important to watch them during functional testing so you don't cause a problem. Always be aware of your surrounding. Always rely on operators or contractors to determine if the system is safe to operate. Always allow an operator or a contractor to start, stop, or change parameters of the system. Remember, these systems do not belong to you, and a liability may be incurred if something goes wrong. Always verify lockout, tagout if entering beyond a safety barrier of a machine. Always warn of an unsafe condition if life safety issues, even if they're not the system you're testing at the moment. Remember, safety is everyone's responsibility. Please be safe. Types of FPT testing. Okay, so first type are manual test. Now, what I mean by manual test is you make something happen and you watch it. That's really basically it. So is where a commissioner observes the reaction or response of a control sequence. Most manual tests are similar to point-to-point tests, but are more complex. Manual testing may be one of three different types. General mode tests. General mode tests are where you observe a system reaction to a sequence or a control state, or change of state. An example would be if you place a system that is in cooling mode into heating mode and observe the heating valve begin to open and the cooling valve close. So that's a manual observation. Another example would be when you are on site prior to occupancy and observe the system enter morning warm-up mode and verify component or set point reaction. And like manual mode would be if you turn on an exhaust fan, it comes on, but we've probably already done that point-to-point test, so we wouldn't need to make that a functional test. Then there's truth table tests. Truth tables are used to verify complex sequences of staged equipment with many operating modes. You create a matrix table to make it easy to record the system reaction in the field without making mistakes. So what happens, you make a tables, because when they're so complex you can't keep track of them, you need to have something to remember. Here's an example. This is a surgery chiller. In other words, this chiller doesn't run all the time. It only runs in the winter mode. And what happens is a lot of large hospitals, they economize their chilled water temperature during the winter time so they don't have to have as cold as water because the air handler doesn't need the load because it's not hot outside. Well, during these times, we might bring a surgery chiller on because surgery still needs the real cold water, chill water. So we bring on an normally we bring on an air-cooled surgery chiller during the winter modes when we got outside air temperature that this air-cooled chiller can really make cold water for the surgery suite, and the rest of the whole hospital can have elevated chill water temperature, which saves them a lot of energy. So here's the problem. This little diagram is not obvious what these valves do. I mean, you can kind of tell, well, they're going to isolate it, but there's actually three operating modes here. If you look at this here, there's three operating. Let's get that back. The first one is run on central plant only, and the second one is run on standalone mode, and the third is run in booster mode. So in other words, we can run if we have let's say we had 50 degree chill water temperature and we need 42 degree water to the surgery chiller. So what we would do is this is going to the surgery. This is the main central plant coming in. So if you want it to not flow any water from the central plant and this chiller, so it actually circulates water this way, this pump. So this valve's closed and this valve's closed. So now we're operating as a standalone chiller. If we want it in booster mode, which now that's more complicated, it takes water from this line, and this line is returning. It takes water from there, runs it through the chiller, and then this goes out. So now we're actually mixing water. So this is a complicated process. that's hard to figure out if you don't remember. So these are the chiller. The chiller, it should be off, on. Chill water pump 1 is off, on. And valve 1 is closed, open, close. So it tells you where those are going to be. So when you're out there watching it, the first thing you do is say, well, let's let it run on central plant alone. And then you observe that the chiller's off, the pump's off, and the valves are in the right position. And then you make a change and say, well, let's do it in booster mode. So then you do it in booster mode and watch and make sure the valves are the correct operation. So it's really easy in the field to do these. And it's very important that you do these to make sure these valves work. If these valves are not on or off at the correct time, nothing works. So that's very important. Okay, HVAC functional test, failure mode test. Now, failure mode tests are also very important. Failure mode tests are where you fail a laid piece of equipment and observe the lag piece of equipment startup and associated failure alarms are issued. So manipulate chillers, cooling towers, and pumps. Standby are redundant fans or air handlers. And you just simply make a table and say, this is lead pump 2 starts when we have a pump 1 fails. And so this you'll see, then you just go over here and say reaction 1, and you verify it, reaction 2. First one is the lead 1 pump stops because it failed. Lag pump 2 starts, verification, and we send an alarm. So you verify these 3 items, and you just say verified. And then the same thing is lag pump 2 starts upon lag pump 1 failure. And you just walk through the system and fail the first pump, make sure the second one comes on, fail the second one, make sure the third one comes on, and then make sure it goes back to then you fail the last one and unfail basically the first one, and then refail the last one and make sure it rotates back. And that's just failure modes. You're just making sure it's failure modes. And if your sequence has timers in it, then you verify those timers the same way. Trend functional testing. Trend tests are used to test the actual performance of the sequence programmed in the controller. Trend test scripts are created by the commissioner and the data trend set up by the control contractor. There are 2 types of trend tests. There are short-term trend tests. Short-term trends are used to test fast reacting systems such as supply duct temperature and pressure. Short-term trends are maybe trended for 5 to 90 minutes with intervals from 5 seconds to 1 minute. So basically, these short-term are normally work best if something can react really quickly, like a supply duct pressure set point. You change a fan speed, the pressure changes immediately. Or in pipes, same thing, it changes immediately. So they're normally used for that kind of things that are really short. Supply duct temperature can change very quickly. Pipe temperature, not quite so quickly, can be used, but it takes a little longer. And the timing can be sorted. Now, normally short-term trends are created by you. You actually write the script, and normally the control contractor inputs it right there into the system and creates a trend for what you want to watch. And then you guys sit there and watch it, and then he collects the trend data. These are a little bit labor-intensive, but you can do a whole bunch at the same time, so you can do that. Long-term trends are easier to do because they're kind of automatic. What you do is a long-term trend are used for slower reacting systems such as room temperature and humidity, building pressure, or changes of state of conditions. Long-term trends normally are limited to several days. So these are easier because you can set them up, let them run for a few days, come back, collect the data. So still, someone has to set up the trends for them because the trends aren't ones we run all the time. What equipment gets what type of functional test? So manual test. Central plants, normally it's central plants, start, stop, set points, restart from power failure. Central plant equipment failure modes, which we just talked about. Air handler AC units, auto, start, stop, set points, and occupied, unoccupied, restart from power failure. So these are things that are always done on a manual test. Exhaust fan and terminal units are manually tested during the PFT stages for data trends. Trend test. CP temperature control loops, chill water, condenser water, and hot water reset sequences. Central plant pressure control loops and reset sequences. Central plant economizer temperature loop. Air handler and ACU supply air temperature control loops and reset. Air handler and air conditioning unit supply air pressure control loops and reset loops. Air handler and air conditioning units building pressure control, normally and economizer control. Air handler unit and air conditioning unit occupied. Optimal start stop and morning warm up cool down. Air handler and AC unit economizer control and demand ventilation control. Air handler and AC unit humidity and dehumidification control. Terminal unit temperature control, occupied, unoccupied, heating and cooling. ERU, energy recovery unit, and other HVAC equipment temperature or pressure control. So those are the things you can see the difference here. This is best with long term, and these are best with short term, manual test or short term. And I'll show you what you can do here. Writing test script. Manual functional test scripts, general mode test. General mode test scripts are written by the commissioner for each reaction test. This may be a list of tests written in Excel or Word or by copying standard scripts into a cloud-based piece of software. And this is a typical one that is an AC unit general operation. So you'd say, what's the run status? Verify the system schedule activates unoccupied and occupied. So you verify that. These are manual modes, right? Verify correct set points are used for occupied and unoccupied. So as you switch it from occupied to unoccupied, you watch what set points it's using to make sure those are properly programmed. Auto restart from power failure. You power fail it and see what happens. Make sure it comes back on and how long it takes to get back on. Unit responds with a decrease in supply air temperature to lower room temperature set point. Unit responds with an increased supply air temperature set point. So this one is a manual test, and you're saying, okay, I put it in heat, it went into heating, it started to heat the room. You don't know what hysteresis is, you don't know if it got the set point, you don't know any of that stuff, but you know it's headed in the right direction. Manual test scripts continue. This is truth table tests. So truth tables or scripts are written by the commissioner for each complex system to be tested. These truth tables are written in Excel or field use for field use and are pasted into the final report, or they could be in some other piece of software besides Excel. But here's the one. So this is a central plant startup you see here. So here's a central plant. So place the system in occupied mode, and you see it starts. And you check out what is chiller 1 isolation valve is supposed to open. Primary pump starts. The cooling tower isolation valves open. Condenser pump 1 start. Heat exchanger isolation valves are both closed. Lead chiller CH1 starts. Leaving chill water set point is shown to be 45 degrees. And so this would be a truth table, and you say verified, verified, verified. Okay, other manual tests, failure mode tests, and this is an important one. Test script is written by the commissioner for each failure mode test. May be a list of tests written in Excel or in Building Start or some other program that you might have. So here's a CP chiller failure mode test. So run status, lag chiller 1 starts upon lead chiller failure. 2, lag chiller 2 starts upon lag chiller failure. Chiller 3, lead starts upon lag 2 failure. So this is telling these two pumps fail back and forth. It's just a failure mode. Automatic trend test. Automatic data trends are created for each control loop. A single controller may have several functional trend tests. Components of each trend test are points to be trended. Data trends should be no more than 4 to 6 points trended, or graphs get too difficult to interpret. So what we're saying there is if you're going to trend 4 or 5 points, the graph, you can figure that out. If you want to try to put 20 points on a graph, what happens, the graph actually tries to pick colors and they get too close. It just gets way too complicated to read. So you got to limit the number of points you're going to actually test. Trend interval time. Trend interval depends upon the possible response time of the total system. Short enough interval to make a minimum of 40 to 80 points to be trended. So now you've got one of these points you've trended. You're going to trend it long enough so you get enough points. So let's say the trend interval is actually 1 minute. Okay, then you're going to need to trend that for 30, 40 minutes to get up into some meaningful number of data. If it's every 10 seconds, you won't have to have it near as long, right? So you figure if it's a short-term test, you may be down in the 5 seconds, 10 seconds, 30 seconds, somewhere in that range, so you don't get a total long time of trends. Trend schedule, a description of the anticipated set point response to the point change, and a description of the time schedule. Time before set point change and after set point change. And we'll go over a couple of them so you understand what we're talking about. But these are critical things you have to put in your trend script. Okay, each trend shall have a copy of the specified control sequence for the loops. This makes it a lot easier for the guy out trying to figure it out. Description of each trend point included. Time interval for each trend. Set point values. Trend schedule for runtime. Description of required results. Now here's an example. Now this was clipped out of a different system, but this is a so this is the trend. Now here's the loop. So we're trending a temperature control loop. So this is a temperature control loop. So the chill water valve shall modulate to maintain the supply duct temperature set point. So we're doing a chill water valve that's going to do supply air. So with the trend points are supply air duct temperature set point, actual supply air duct temperature, and the chill water valve position. Now this is commanded position because a lot of valves don't have actual position, so it's commanded position. With those 3 points, we can tell whether this thing is working or not. So that's what we're going to do. So down here, we have the trend points. Then we have the interval. We're going to do this every 5 minutes. So this is going to be a long-term trend, right? This point 2 here is a little bit confusing. It really should have been blank because it's going to be a long-term trend. So as a long-term trend, it would be blank. But what this was for is this was originally written for a short-term trend, and we wanted to increase it by 0.2 degrees, the supply set point. But we're not going to do that. Trend for a minimum of 48 hours. So that's 2 full days. Now here's what's important. Results. A lot of commissioners write pass-fail criteria because they're not actually doing the trends, so they want the control guy to say it's pass or fail. But I don't like doing that very much because to create pass-fail criteria, you can actually get yourself in trouble where it can't possibly pass, so you need to do it differently. So what I do is I normally put in here, and we'll talk about that in a second, supply air temperature reaches set point without excess hysteresis in a reasonable amount of time with a small offset as approved by the commissioner. That's what I normally say. The commissioner gets the response of the trends and he approves them or not approves them. They're right or wrong. This is the one thing you can't approve in a system. Now this other one, this is a supply air reset control. So it's resetting. This is the sequence that resets this particular one. And you notice this is a pretty complicated sequence. It doesn't affect unless the enthalpy outside is a certain level. And then it takes effect. And this would have the supply air duct temperature set point again, the actual supply air temperature, and the duct heaters. This had 3 duct heaters heating there, so we put those 3 duct heaters in there. Now you can put off and on devices in a sequence in a functional test, because what happens when a heater comes on, it goes from 0 to 100%, and you can see those blocks as they come on. So you can see when they come on and go off. So it's legal to do that. You can actually do those. And then we have a 5-minute interval, and of course the set point is variable because it can change during those times. Trend for 48 hours. So we're going to trend it 48 hours again to see it. So remember, you're trending every loop, and a reset loop or a temperature loop or a pressure loop. We're testing those loops and a functional test for each of those loops. Now, some people say, man, that's a lot of tests. Well, it's not as bad as it seems, because say like you got 20 VAV boxes, you can do all 20 VAV boxes at the same time. It's the same deal. And then once it's all done, the control contractor deletes all those trends that he's got in the machine. We don't leave them in there because it takes too much memory. So the automatic trend test continued. An example of a short-term trend is where set points are manually manipulated. So a short-term trend, the control contractor actually comes up, sets up the trends, and then launches the trends and waits the interval time, makes the set point change, waits the interval time, and then ends the trend and prints it out. So that's the way it goes. Now, when you get those kind of trends, the control contractor may give them to you as a data log or as a graph. I actually prefer the data log so I can create the graph. I can just move them into Excel and create the graph. The reason I don't much care for them to do the graphs is because they might manipulate the time interval or manipulate the spacing on the axis, which can make it look better or worse. I mean, hysteresis is the one that drives everybody crazy, because you can make a graph so long that you can't see the hysteresis, but you make it real short, you see it right away. So I want to be able to change that. And if they give you a graph, you can't. But if in a Excel file, and we do a graph, I can change the interval on that graph easily and see if there really is hysteresis. Anyway, here's a short-term trend. This is a room temperature. It's probably a VAV box. So it's room temperature, supply set point, actual room temperature, damper position, supply air temperature, and heater amps. So this is a VAV box. We're going to look at it every 15 seconds. The set points is room temperature at 75 degrees. And here's our schedule. So trend for 5 minutes at existing set point at 55 degrees. Raise set point up 5 degrees and trend for 30 minutes or until the set point is achieved. So what we're going to do is we're going to take this existing set point and then we're going to raise the temperature to get it into heat. So now we're going to watch, make sure this heater comes on. And then after that, after it's got the temperature set point, because we want to know how long it takes, then we're going to dive it down 8 degrees. So we're going to put it below its originally set point and put it into full cooling. And do that for 30 minutes or until the set point is achieved. And then return the set points and let it run for 15 minutes to see what happens when it settles down. So remember, this is a short-term trend, so the control contractor is right there running this, and you're there supervising the observation. So basically, he can make set point changes and do all that because he's right there at the console during this trend. The results: room temperature reaches set point without excess hysteresis is a reasonable amount of time and with a small offset or approved by the commissioner again. That gives me the authority to actually look at this and tell whether it works or not. Short-term trends are 5 seconds, 15 seconds, 30 seconds. It can be anything. Now, one thing that's really critical is that in a trend, within this test trend, all of the points have to be trended at the same time. So you see these trend points? The contractor is going to set a trend up for each one of these, and he has to do an interval for each one of them. So make sure it's all the same. If you made this one 15 seconds, and this one 30 seconds, and this one 10 seconds, putting them together is almost impossible. It's possible, but it could take you a couple of hours to do that. And by using a special piece of software to do that, it's just not worth it. Just make sure they're all the same interval. So for this test, the interval is 15 seconds. That means all of these are set to 15 seconds. A key point to make sure you have a minimum of 40 to 80 data points. So each of the set points will allow adequate settling time or reaction time. 20 minutes for a 15-second interval. So that should be fine. Okay, so now a test script. Continue for short-term. An example of a short-term manual trend where set points are manually manipulated, no DDC control system. So let's say you have a job that has programmable thermostats and they want you to test that. Well, you do it with a data logger. You take a temperature and humidity data logger and you put it right at where the thermostat is. And then you do this. This is a data logger. Place the data logger near the thermostat. Program the data logger for temperature recording at a temperature and humidity interval at every 15 seconds. You set up the data logger for your interval, 15 seconds. Log at existing set point at 75 degrees for 10 minutes, and then raise the set point 5 degrees. Trend for 1 hour minimum. Lower the set point 8 degrees and trend for 1 hour minimum. Retrieve the data logger and return time set to its original set point. The letters are too small for me to read, let alone you. Okay, so this is down here is where you record the data. Put your logger number in there so you don't need what logger is, the date of when you're doing this, and then start time and the temperature. So your first point, temperature, and then this is your adjustment 1 time when you went in and added 8 degrees to it. And that's 10. And then the second adjustment is when you put it way down there, did that, and then stop time. And that'll see you trend up. If you have more of them, you put more of them in there. If you have more points and start times, you do more of them. But this becomes a data log record, and then you print out the trend from your data logger and attach that behind it. So this is just as good as an automatic control system doing the data log, except you're doing it with data loggers. Key point is to make sure you have a minimum of 40-80 points, each point to allow an adequate settling time or reaction time, 10 minutes and 60 minutes for this example. When designing trends, remember a high mass room may take a long time to change temperature. So you need to understand, if you're doing a museum and it's got concrete walls, you need to check to see how long it takes to make a temperature change. So you don't want to go 10 degrees up because it may never get there. You might, in that example, you may say, okay, we're going to do a 2-degree upset point, and we're going to watch that and it may still take an hour to do 2 degrees. So you have to be careful with that. Now, in a regular office building, it don't take very long to change. It may take 10 or 15 minutes to change, but it's something you need to be cognizant of so you don't write a test that can't pass. It's really embarrassing if you write a whole bunch of tests and the control contractor and they all fail, not because he failed, but because you failed. So you have to be careful with that. And these are the time for short term, again, 5, 15, and 30 seconds. Automatic trend tests for long term. Now, long term are a little different. An example of automatic long term trend where set points are automatically changed as a part of the sequence. So what we do is we set up a trend. This particular one is a chill water temperature supply. The DDC contractor shall trend the actual chill water temperature set point, and the chill water actual temp. Actual outside air temp and chiller amps. Trend shall be 5-minute intervals with a minimum sample time of 576 data points, 48 hours. The CXP is to analyze results components compliance chart to be attached to the report. So we're going to look at the chill water supply temperature. We want low hysteresis, and we want a small offset, and we want short time. Now this is a long term, and we normally write this the same as we would the short term, except we use long term points. And so what happens is this works best if you have a sequence that actually changes a set point, like occupied and unoccupied mode. And you do 48 hours, you're going to get 2 days in there, or at least 1 day in there, where we're going to change a set point for occupied and unoccupied, and you can see if the system actually gets there. And in these trends, when you do a bunch of them, you can see how long it takes for the system, once it goes into occupied, how long does it take to get the set point from a setback set point. So these are trends that tell you how to do that. The test is acknowledged to the test scripts or report, but the data trend is inserted into the final report as a PDF. Long-term trends cannot be supervised by the commissioner, so you'll have some failed tests due to the contractor not knowing what a failed test looks like. But if they're long-term trends, you're not going to be there. Now, long terms could be 1 minute, 5 minutes, or 15 minutes, not longer than that. Performing manual tests, general test modes. With a clear understanding of the needed test, or with a test script, the commissioner observes test as schedules. Set points or other operating parameters are adjusted to cause the system to change operating modes. The commissioner observes long enough to prove the system responds in a correct manner. This validates the following. The polarity is correct. Beginning response is correct. Unit is correctly connected in the graphic. Set points are easily overridden or changed. General mode tests do not validate the following. The loop is properly tuned. Because you're manually observing it, you can't see a hysteresis. Reset sequences are working correctly. Do not provide proof of performance other than I said so. So if you're doing a manual test and you're observing it, you're going to put in there that I observed it. Now, if you need to have better verification of that, you need to have an owner's rep with you. Because the owner's rep is a lot more weight than you. If he says, yeah, I seen it work too, then it's better. But for just you saying it, okay. But, it's just like everything else. That can be suspicious. Okay, truth test tables. With a script, the commissioner observes tests as schedules, set points, or other operating parameters are adjusted to cause the system to change operating mode. I'm trying to get back into the screen here. Commissioner is observed long enough to prove the system responds to a correct manner. This validates the following. Each device or piece of equipment responds correctly. Unit works correctly for each operating mode. Graphic response matches the actual field condition. Truth tests do not validate the following. Do not provide proof of performance other than I said so. Systems that have several operating modes should not be tested by trending. It becomes very hard to interpret the trend, and many start, stop, open, and close set points. So that surgery chiller, you couldn't do that by a trend. You could, but boy, interpreting the trend would be difficult. It's much better just to observe it actually happen. Manual test, again, this is a failure point testing, really important for the quality of the commissioning. With the test scripts, the commissioner has an operator or control technician fail units to cause a standby unit to operate. The commissioner then times and records the reactions in accordance with the test script. Normally you walk through each unit in sequence and then reset the lead unit and test rollover from the last unit to the original lead unit. Need to check for components stage in the correct sequence with the correct timing. Must pay attention to any timers in the control circuits or sequence. Started machine continues to use the correct set points. Failure tests do not validate, do not provide proof of performance other than I said so, unless you have an owner's rep with you, like I just said. All right, automatic FPT tests use the control system to provide data trends, provide functionality is the best way to accomplish complicated or very important system tests. These are two ways to accomplish a test. The first is to have the control contractor set up a data trend that matches your test script, then watch the trend as time passes to see the test results. If it works correctly, you can save the data trend to print out into a final report. This is a short-term trend. The second way is to create a program that creates a data trend to match the test script so that when the name or address is changed, it can be run for different pieces of equipment. This is the preferred way because when this program is saved on the workstation, the operations can also run the test in the future without having to set up the test trend. So what is kind of like a little applet control sequence, and the programmer writes this little program, and it just say like for a VAV box, he would write the sequence test for all the loops within a control box, and it would have an address. It would be the VAV box address in the control system. If he brings that up and changes that address, all the points change to that new box. So these are really handy because the control contractor only has to write the program. He doesn't have to write every data trend. Otherwise, he has to manually set up the data trends. It depends. Some guys can't do this. Some systems can't do this, but a lot can. And this is really handy to have because now the owner can have it, can always run those functional trends in the future. Automatic trend testing. Short-term trend tests. Short-term trends work best for variables that change quickly within a few minutes. Control technician initiates the trend points at the specified time interval and then makes set point changes to match the test scripts. Once complete, they save the trends as a data log or trend graph. Many systems can be done at the same time. Short-term or more labor intensive, but short-terms are more labor-intensive, but you can see the results immediately. Short-term trends are normally used for VAV terminal units, supply air temperature, humidity, and pressure trends, pipe chill water and hot water temperature, pressure flows. Long-term trend tests. Long-term trend tests work best with variables that change slowly, many minutes. A control technician initiates the trend points at the specified time interval and then runs the trends for the length of time specified, usually 7 to 14 days. Once complete, they save the trend as a data log or trend graph. Many systems can be done at the same time. Long-term trends need a sequence that changes a set point to show the trend response. Normally this is an unoccupied set point change. Long-term trends can be used on any loop that has an automatic change in set point. Long-term trends are normally used for economizer trends, room temperature and humidity trends, reset sequences, morning warm-up and cool down trends. All right, let's look at a automatic trend, and we're going to look at exactly what they look like and what they're comprised of. So this is a reaction to a set point change, produces a resulting control action with a small amount of hysteresis, with a small offset over a reasonable amount of time. That's what we're after when we're trying to trend a loop to see what it's doing. So this is an output of a trend of a point. Now this is a training item. It's not actually a real trend, and the reason is because it's perfect. You will never see one like this. I have never seen one quite like this because it's perfect in every aspect. So here's a little bit what we look at here. You'll see that this is a trend general and it's have one point. If it's a hot water coil, it's probably a VAV box, but it's just doing the hot water loop is all it's doing. So this is the set point. You can see it was set at 65 degrees and it's come along. This is the trend is moving in time, and at this point in time an operator makes a set point change and takes it to 75 degrees. So this is this kind of whatever color that is, that's the set point. And this down here is the valve. This is what the valve is actually doing. So the valve is kind of cruising along. It's closed because this temperature was satisfied at 65 degrees. So this is closed. And then the difference between this and this is the reaction time of the valve. So it takes a few milliseconds or seconds for the signal to get through the controller and tell the valve to do something. So the valve now starts cruising up, opening to get more heat in the space to get to the 75 degrees. And when it gets here, it actually overshoots. So now it's trying to change its mind and come back down because now the controller sees the temperature is rising. Doesn't show it, but it does. Comes back down, and it kind of does a couple of loops here until it settles out. And this is the settling time. This is what we want to be as short as we can. And then this is the offset from the actual temperature of the room. Okay, this blue one is the actual temperature of the room changing. And this is the offset right here. We always prefer a positive or offset, but it might actually be a negative offset. It doesn't really matter. So what we're trying to do, the data trend is trying to show, number one, how fast this gets here, how much hysteresis, this bumps, and on a normal trend you'll see it do this and then settle out. And if it's one that's not in tune, you'll see it do this. And that's what we're trying to see, is this hysteresis, to see how well this loop is tuned. So when you actually tune a loop, is to kind of explain, the controller is using mathematical algorithms on trying to tell it what to do to try to come up with this few hysteresis and that small offset. So it's making a bunch of adjustments to try to do that. And in this algorithm, there's three basic pieces that it's calculating. One is the proportional band, which is how fast this slope actually reacts. Does it react really fast or does it act really slow? And that's the proportional band. The second one is the integral band, and that actually is calculating the area under these curves. Between this line and this, it's calculating the areas of the curves. And what it's trying to do is, under each successive one, it's trying to make it smaller. And the final one is the derivative band, and it's actually telling you what the slope of this line is. And it's trying to get this slope to be flat. So those are the calculations. And when you actually tune a loop, you change some constant factors in each one of those parts of the calculation. So this is not easy to do. And we have a video, it's called C7 in the control block. It'll tell you how to do this. It's complicated, and the control contractor should know how to do that. If not, you may have to kind of help him, show him how to do that. Some control guys don't tune them at all. They just say, well, it'll tune itself. Now, there are controllers that have self-tuning blocks. Now, that's not what it sounds like. A self-tuning block is designed to make real small changes to catch up to any changes in the system. Now, this program that you've tuned, is that you tune it, but the reason you tune it is because everything is slightly different. The reaction of the valve, the reaction of the controller, the reaction of the room may all be different, and when that changes, you need to make real minute changes to make this more better, right? To make it perfect. So what happens is those controllers that have self-tuning will actually constantly make real tiny adjustments, but they will not tune it to start with. You have to get it somewhere in the bound. You have to get it so it's actually working before this self-tuning will take over and do a little bit of fine-tuning to it. So no, self-tuning doesn't tune it by itself, so you don't have to look at them. You need to look at them because they'll never get there because they're making such small, minute changes. You need to get it in the ballpark first. So that's how we trend. There's the training video C7 for DDC controls to tell you how to actually do a loop, actually train it. Actually trains you on how to actually get this program adjusted. It's not as simple as it sounds. It's more complex, and that's why there's a separate video on it. So now we're going to look at some possible issues you might run into and what you do with those. So the first one we're going to look at is if you have 2 or more units that are in the same space, they must be tested at the same time to prevent fighting each other. So if you have a room, big room, it has many VAV boxes in it, it's just one room, like an open office concept, then you're going to need to test them together, because if you have one box and another box right next to it, one's in heating and one's in cooling, they're going to fight each other, so you don't want that. So you need to do them all at the same time. So, and you can do many units at the same time, even if they're separate rooms, separate offices, because the points, it's just a control system, so they can collect those points at the same time. That's not a problem. If the structure has a high mass, the trim must be much longer. You may have to pre-test the space to see what the change time is prior to writing the FPT test scripts. If you don't know, if you suspect it's a high mass building, ask the control. Let's do one just to see how long it takes. Once you have that data, now you can write all the scripts. If a system has a design issue or a point-to-point test was not done successfully, the functional test may not be meaningful. Be careful when writing pass-fail criteria, because the condition may take the test past your criteria, making the test invalid. Normally, I use results of the FPT test to be analyzed for compliance by the commissioner instead of saying pass-fail. But it's really dangerous to write pass-fail. Okay, functional test possible issues. Receiving the data log from a control contractor are referred so that the data is identified. If you just get a graph, the control contractor may have manipulated the interval or try to hide hysteresis, or may not know. So it's much better to get a graph, a data instead of a graph. Of course, you have to spend some labor then creating it, but what you can do is set up a template in Excel and you just import the data, and it comes right in and does whatever you want it to do without a lot of time. So that will help. Make sure the contractor uses the same interval for all trends. You want to interview at one time. If not, it becomes very difficult or impossible to put them together. Failed functional tests. Functional tests itself failed due to incorrect script or was not set up correctly. This is your problem, and that's not good, but then for this, the test has to be run again to revise the script and do it again. Functional tests failed due to control point interaction or inaction or wrong points trended. This is the control contractor's problem, and then it's got to be done again. Your script may be right, but he's going to have to do that test again. Okay, controller system fails to provide correct response during the functional test, so it just doesn't work. System cannot meet the test parameters. Issue must be analyzed to determine if the test is the issue or the system is the issue. If the system is the issue, then you got to go into an issue log and try to figure out what's wrong with it, and it has to be corrected. It may just be a programming change, maybe something else. Okay, system size, type, or installation is incorrect. This failure means a base system correction normally taking time and money to fix. Finding this kind of issue so late in the project makes the commissioning provider and the commissioning process suspect. So what I'm talking about here is that you get into a test and the system is not capable of doing anything to prove functionality. It just doesn't work. I'll give you for an instance. I was doing a data center and I never paid attention to the humidifier for the computer room. This was a long time ago, but this is when we had Cray supercomputers, and this job had Cray supercomputers in the space. And it was a fairly good size unit, but I didn't pay attention. I never checked size of units. Well, what happened, this particular unit was like 10 times too big. And the engineer had it put on a step sequencer. So it had 4 stages of humidification because it had electric cowl rod heaters that brought on steam, and it had 4 stages. And they were large, they're big kW apiece. And so the control system would say, okay, I need humidity. So the control sequence started the first one, and then went to the second one, went to the third one, went to the fourth one, and then it would shut them all off. So what had happened is the control room said, I'm a little low on humidity, I need humidity. So that big old humidifier, which is 10 times too large, came on and went through the first stage, then went to the second stage, third and fourth stage, and poured water on the computers. It poured water out of the duct. Boy, that got everybody excited. Well, the problem is that unit took 3 months to fix because they had to re-engineer it. They had to order a new unit, had to rip that out. I supervised changing the controls to an analog output. We made sure that wasn't a step sequence. The humidifier, being 10 times smaller, didn't have to be. So what happened here is it delayed the opening of the project. And it was all because we didn't take time, or we just didn't know to look at this. We assumed the engineer had the correct size. I don't normally check size of equipment we're doing submittal, and we didn't check it on that one either. So anyway, that's a story. But we don't want to miss things early on. And some people who don't do site inspections, I think they're going to get into this lot. So this is not a good thing because it reflects poorly on you. Manual reports. How do you report a test? Complete FPT test scripts form by filling in the verification cells. Attach the FPT trend PDF behind the test script. If it doesn't have a data trend, then you just use this as a report. Cloud-based software produce automatic FPT test reports allowing for all FPT pass-fail indications. Attach the PFD, the functional test trend PDF behind the FPT report. And that's all these are. These go into the other part of the report. So this is not difficult and easy to do. All right, that's functional testing. You made it all the way through that. I hope that was helpful in understanding how to do that. If you need any questions, you can put them down in the comments, and I'll be sure to answer those. So I appreciate you being here. I appreciate you listening to the videos. Have a great day. I'll catch you on the next one. Thanks.